So in this video, we'll be covering the other fundamental forces. So you might have heard of the gravitational and electromagnetic forces at school, but many people don't know that there are actually two other fundamental forces, the strong and the weak nuclear forces. And these two forces are actually two different forces that each play a separate role in the nuclei. The strong nuclear force is an attractive force that pulls protons and neutrons together to create the nucleus of an atom. On the other hand, the weak nuclear force causes the radioactive decay of the nuclei.
So, introducing to the weak force, which specializes in the radioactive decay of subatomic particles. So what is the weak force? It is a fundamental force of nature that's apparent in some forms of radioactivity. And it governs decay of unstable subatomic particles. It initiates nuclear fusion reactions, which are used to fuel the sun. And it also causes a literal change of one subatomic particle to another. And then it's one of its most important functions is that it's responsible for producing the energy needed for most life forms here on Earth. So how are these weak force interactions formed? Well, force carrying particles called bosons reside in subatomic particles like protons, neutrons, and electrons. There are two specific charged particles called the W and Z bosons, which are exchanged between subatomic particles when these particles come within a threshold distance of 10 to the power of negative 18 meters, or 0.1% of the diameter of a proton. As a result, these subatomic particles decay into new particles. And a special thing to note is that weak force is not a binding force like the other fundamental forces, but it's a force that transforms a subatomic particle to another. So examples and uses of weak force interactions include beta decay, which is converting neutron to proton or vice versa, electron capture, which uses an electron to convert proton to neutron, nuclear fusion, which involves fusing two lighter nuclei to make a heavier nucleus. And the heavier nucleus's total mass is actually less than the total mass of the lighter nuclei. And so then the leftover mass is released as energy in the process. And this occurs to fuel the sun. And then it's also used in archaeology. So archaeologists use carbon-14 to date artifacts by analyzing the rate of decay of carbon-14 to form nitrogen-14.
Now let's talk about the strong force, which on the right scales is the force with the most power out of all the other fundamental forces. It's responsible for holding subatomic particles, so like protons and neutrons, together with each other, and also holding together the quarks that make up said protons and neutrons. So the strong force, to talk about the strong force, you really have to know this concept called color. And now color, much like spin, it doesn't actually relate to the actual color of a particle, but it's instead just a virtual type of property that doesn't actually correspond to a real life color. So quarks, these particles that you see in purple, do have color, and bosons as well. Leptons, particles similar to an electron, do not though. The strong force is only really visible with among particles that have colors. Now, you may know that the photon is the mediator of the electromagnetic force. That is to say, the photon makes the electromagnetic force happen. Well, with the photon, you have this other boson called a gluon. Gluons make the strong force happen. So you can think of the strong force as pretty analogous to the electromagnetic force. Gluon is the photon and color is the charge. Now, the situation where the strong force and the electromagnetic force differ is how they scale with distance. You may know from your physics class that the electromagnetic force decreases the further away the two particles get from each other. However, the opposite is true with the strong force. Because the gluons that make up the strong force themselves have the color property, unlike photons, which do not have a charge, the strong force increases with the distance of particles. So as you get further and further apart, the force pulling them together is actually increasing. Very interesting. You can think of this as similar to how a rubber band pulls harder and harder to get back together, the more you stretch it further and further apart. But of course, this is up to a point. Soon the rubber band would break, and soon the strong force does not actually have any effect anymore. This is because the strong force is mediated by the exchange of mesons. So, and these are responsible for how the strong force ties together atomic nuclei. Mesons are subatomic particles made up of a quark and its corresponding antiquark. If they're very short-lived particles, only existing for a couple fractions of a nanosecond at a time, but hadrons, which are particles made up of quarks, exchange these all the time. And this exchange of mesons is what ties them together via the strong nuclear force. And this strong nuclear force, if we did not have it, nuclei of atoms would basically not exist. Because nuclei are made out of positive protons and neutral neutrons, the overall charge of a nucleus is very, very positive. And since the like charges repel, that means based on the electromagnetic force alone, a nucleus would have no choice but to, explode. But the strong force ties the nucleons together. Because both protons and neutrons can exchange mesons with each other, they're tied together by the strong force. And on the subatomic scale, the strong force is much, much stronger than the electromagnetic force, about 100 times so. So this means that even though there's the electromagnetic force trying to push the nucleus apart, the strong nuclear force ties the nucleus together. Now, the strong force also has a role in quarks. Gluons, which we've talked about before as the particles that mediate the strong force, responsible for gluing quarks together. The quarks are almost never come apart because of this strong force interaction. The only way you can see them come apart is if you were there at the Big Bang, or if you're inside the center of a star, or perhaps for brief moments of time inside of particle colliders.
So, the similarities and differences between strong and nuclear forces. A similarity between both of them are that they're involved with atomic physics as they specifically affect the atoms and their nuclear structures. The main differences between the two is that the strong force deals with the attraction within the nucleus as it holds the protons and neutrons together, whereas the weak forces causes radioactive beta decay via the conversion of protons and neutrons. Specifically, the strong force is short range and strong in terms of the force exerted. It's actually the strongest force out of the four fundamental.
So these are our citations, and thank you for watching.